Okay, welcome to another Mr. Weis Solves an Old AP Problem video. In this problem we'll be doing the 2008 AP Calculus BC exam, problem number 4. This is a motion problem, so very similar to stuff you should be doing in your homework these days. So let's see the setup. A particle moves along the x-axis, so it's 1D motion, it's moving back and forth along the x-axis, so that its velocity at time t for the first 6 seconds from time 0 to time 6 is given by the differentiable function v of t, whose graph is seen here. A couple of facts about this. The velocity is 0 at the origin, it's 0 at time 3 and at time 5. We also know that the graph of the velocity has a horizontal tangent at time 1 and another horizontal tangent at time 4. We're also told that the areas bounded by the t-axis and the graph here, these areas are 8 from time 0 to time 3, 3 from time 3 to 5, and 2 from time 5 to time 6. Finally, we're told that at time 0, the particle starts out at a position of -2. So it's 2 left from the origin, whatever the origin is defined to be. And I'm going to let x of t be the position of the particle at time t. So in other words, dx dt is the velocity graph right here. Okay, so what does the question ask for part A? It says for this time, from time 0 to time 6, find both the time and the position of the particle when the particle is furthest to the left. So we want to know when does the particle get furthest to the left, and how far to the left is that? So just spitballing here, playing around. Note that at time 0 the velocity is 0, but very quickly the velocity becomes negative. Immediately after the 0 second, the velocity is negative. So the thing is moving to the left, okay? Starting out at a position of -2. So it's moving to the left for a while till it gets to time 3, then the velocity is positive, so it's moving to the right, and then it's moving to the left again. So, awesome. So what part A is really asking us to do is to find the absolute minimum of the x of t function on the interval from 0 to 6. So it wants to find the absolute min of x of t on 0 to 6. That's ultimately what it means. To be furthest to the left means that your x thing, the thing that's keeping track of your position, is as small as it can possibly be. So far, the only value we know is -2. But thinking about it, we know we're going to move to the left of that. So the way we find absolute mins is the way we always do for any problem. What we're going to do is we're going to take the derivative of this and set it equal to 0 or does not exist, finding all of the critical numbers. These are places where the derivative could change sign. These would be places where the function could be changing from increasing to decreasing, and thus are maxes and mins. So we're going to take the derivative of this, so dx dt, but that is precisely the velocity. When does the velocity equal 0 or does not exist? That's what we want to find out. Equals 0 or does not exist. The velocity always exists, so we do not have to worry about that. But we know it equals 0 at 0, 3, and 5. So t equals 0, 3, and 5. So now what I'm just going to do is I'm going to find the position at these 3 places, 4 places actually, because I'm also going to include time 6. And whatever one has the smallest x value, that's our winner. That's the furthest it ever goes to the right. So some of these are pretty easy to figure out. We already know that x of 0 is -2. X of 3. Well, how can we figure out what x of 3 is? Well, x of 3 is the integral from 0 to 3 of the velocity plus x of 0. This is simply, you can see this, we do this quite frequently. If I move this to the other side, you should see that x3 minus x0, which is the displacement, equals that integral, just by the fundamental theorem of calculus. So all I'm doing is moving that x of 0 to the other side. But we already know these. The velocity from, the integral of velocity from 0 to 3 is -8 plus -2, which is what x of 0 is -10. So we've got our first possible winner. if we think about it, actually, it's probably going to be true that this has to be the winner. We'll see. Like, for example, I kind of already know that x of 5 is going to be smaller, is going to be bigger than this, not as negative than this. Why? Because the velocity is positive. From 3 to 5, we were moving to the right. But I'll calculate it anyway. It ends up equaling the integral. We can now actually go from 3 to 5 if we want. From 3 to 5 of the velocity plus x of 3. But this ends up equaling, let's see, from 3 to 5 the velocity is 3 plus negative 10 is negative 7. Not going to be a winner. Finally, I should calculate x of 6. Now this could actually do it, because now we are moving to the left again, so we're moving backwards. The question is, do we move back far enough? And hopefully you can see right away that the answer is no, but I'm going to calculate it anyway. So we're going to do the integral from 5 to 6 of velocity plus x of 5. And this ends up being negative 2 plus negative 7, which is negative 9. And so, the answer to this question is, at time 3, position is negative 10, and that is the leftmost. And that's the answer to part A. Okay, now we're going to tackle part B of the 2008 AP Calculus BC number 4. I've left the work up for part A because it's going to be very useful for what we're being asked to do. So again, we have this particle that's moving on the x-axis, left and right. It starts out initially at a position of negative 2, and its velocity at any time is given by this beautiful continuous function where we know a bunch of cool stuff about it. In part A, we actually figured out where the particle was at time 0, times 3, time 5, and time 6. These were all the possible extreme values for where the position could be. So this was the initial value, this was the final value, and that's what made this interesting. These two places could have been absolute maxes or absolute mins. In fact, negative 10 was our absolute min, and I guess our absolute max is negative 2, but negative 7 could have been one. Okay, so what does part B ask, and why did I leave this up? Part B is pretty interesting. It simply says, for how many values of t on the interval from time 0 to time 6 is the particle at x equals negative 8, and explain your reasoning. I'm not going to write a lot down here. I'm going to say this stuff out loud, but I'm going to talk it through. So the important thing to realize is that this particle is moving in a continuous fashion along the x-axis, back and forth. And we know all of the times when it's moving forward, all of the times when it's moving backwards, that is right and left. We know all of those times. We know that it starts out at position negative 2. We know that it moves left for a while. We know that it moves left for a while until it gets to time 3. Then it starts moving forward for a while until it gets to time 5, and then it starts moving backwards again. We also know where it is at all of these times. And when it's moving forward, on the intervals when it's moving forward, which is from 3 to 5, it's moving forward that entire time. It may be speeding up, it may be slowing down, doesn't matter, it's moving forward. And from time 0 to time 3, it's moving backwards. What we say is that it's moving monotonistically or something like that. Yeah, monotonically, I guess, is probably what we would say. Cut all that. What we say is that it's moving monotonically. Mono meaning one, and it's not like changing direction. We know when it's changing direction precisely. Okay, so when is it at negative 8? Well, it goes from negative 2 to negative 10, moving backwards that entire time. So it must go through negative 8. Hits it there. Then it goes from negative 10 to negative 7, moving forward that entire time, and must hit negative 8 again. Then it moves from negative 7 back to negative 9, and must hit negative 8 again. So I believe the answer is 1 time, 2 times, 3 times. The particle is at position negative 8 3 times. 1 time between 0 and 3, 1 time between 3 and 5, and 1 time between 5 and 6. And that's mine. Okay, here we are doing part C of the 2008 number 4 Calc BC exam. We're analyzing the behavior of a particle that's moving on the x-axis, left and right. So this is right, this is left. It's moving in a continuous fashion. It starts out at a position of -2, and its velocity at any time is given by this function over here, which is continuous, and we know a couple of values about it. What part C asks is the particle speeding up or slowing down from time 2 to time 3? So from 0 to 3, are we speeding up or slowing down? Okay, so this is a standard question, and we talked about this a lot in class. To decide if something is speeding up, it is not enough to look at the acceleration. The acceleration tells you whether the velocity is increasing or decreasing, but just because the velocity is increasing does not mean you're speeding up. It only means you're speeding up if you happen to also be going to the right, going forward, and your velocity is increasing. If you're going backwards, you want your velocity to be decreasing if you want to be speeding up. Ultimately, what it comes down to then is deciding when the velocity and the acceleration have the same sign. If they have the same sign, for example, if they're both positive, that means that you're moving to the right and you're going faster. If they're both negative, that means you're moving to the left and you're going faster. You're in reverse, but your foot's on the gas pedal. So, and if the velocity and acceleration have opposite signs, you're slowing down. So the question is, from time 2 to times 3, is the velocity, do the velocity and acceleration have the same size? Well, let's sign. Well, let's see. V of t is definitely less than 0 on the interval from time 2 to time 3. And the acceleration, which is the derivative of velocity, which is the slope of the tangent line, is clearly positive. So we are slowing down. One way of thinking about it is we're in reverse, but we've got our foot on the brake. Hopefully we're looking behind us as we drive, but we've got our foot on the brake as we're doing it. And that's the answer to part C. Okay, we're on the final part of the 2008 AP Calculus BC exam number 4. We're analyzing the position and movement of a particle that's traveling in one-dimensional motion on the x-axis back and forward, or right and left, whose velocity is given by the function that they give us over here. For part D, I think we're on now. Yeah, part D just says, when is acceleration negative? This is a very straightforward and simple problem. So acceleration is the derivative of velocity. So A equals dv dt. And this is velocity. So we simply need to find out when is the velocity negative. When is the derivative of velocity negative? And we're told that it has a flat tangent line here at 1 and another flat tangent line here at 4. So I believe acceleration, the slope of the tangent line to velocity, is therefore negative from 0 to 1 and from 4 to 6. Whether or not you include these endpoints, I do not think matters. I would just as soon not include them, but I don't think that it matters very much. But that's the answer. I might add a sentence here that says something like, because the slope of the tangent line to velocity is clearly negative there, something that shows why you got this.